diving. And stop when you get to number 2 there. Do any part of it you can, and it's no big deal if you don't get it all. And it's a little bit hard to read, I think, on your photocopy, but it should be fairly legible. Are people approaching the domain and range? No rush. And if you have to leave something blank, leave it blank, please. Don't stress over it, because we're about to fill it in anyway. Alrighty. Okay. A bunch of you are going to do this first one because you have a graph, right? You're going to say that the dependent variable is what? What's the dependent variable? Depth. And what's the independent variable? Now, I'm going to now ask why. And these are the reasons that I'm going to get. Because time's on the x-axis. No one was going to say that? Good. The next reason that I usually get is, because yesterday you said time is almost always the independent variable. Good. What's the reason? Yeah. Time never stops. Whereas you can stop going deeper. You can stay at the surface. Okay? Everybody good? All right. So now, how many minutes did the dive last? 30. Oh, I didn't fool anybody with the scale. Somebody always says 29 there. Darn. At what times did the diver stop her descent? 10 minutes to 14 minutes. I agree with that. Is there any other time? 4 to 8. Now, how is that manifested on the graph? The horizontal line. Why? If she wasn't moving, why do I need a line? Because time never stops. Right? And what else does time never do? Go backwards, unless you have a plutonium-powered 1988 DeLorean, which none of you do. Sure, Beryl, why not? That Cap'n Crunch will get you every time. Okay, now this is the next thing that screws kids up. What was her greatest depth? 20 meters. But a lot of you guys, not you guys because you're smart kids, a lot of people say, oh, Mr. Myers, if she's diving under the water, why does the graph go up? He made funny faces. Understand? What is a graph? It's a representation of data. Is it a drawing? No. Okay. Okay. I'll give you lots of examples of that in a moment. But don't make that error. Motion or something in real life doesn't necessarily look like the line on the graph. Okay? Okay. And let's keep reading. How long did she spend at that depth? 4 minutes. She got there at 10, and she started coming back up to the surface at 14. All right? Now again, there's always a kid that says, if she's coming back up, why is the line going down? I'm not joking. Someone always asks. Don't be that someone. Think before you speak. That being said, you may ask if that is the case. But do not get belligerent about it, because that makes you look silly, and none of you are silly. And finally, the domain and range. This is a problem, sometimes. What is the domain? 0. Is 0 included? Yes. To what? 30. Could I write that any other way? Yes, I could have 0 less than or equal to. Would I put an X here? What would I put here? Time and 30. Cool? Can it be every real number? Yes, even if we don't have a name for it. She doesn't just disappear and miraculously reappear the next second, does she? Right? She's there the whole time. And what's the range? Range is tricky. 0 to 20. 0 less than or equal to depth, less than or equal to 20. Is it all real numbers? Or does she swim down to 10 meters and then disappear and show up again at 14 meters down there? It's all real numbers. Everybody good? Good. You guys make me so happy. Now, reverse it. Here's a graph. This is not drama class. This is not English class. You needn't have rising action and person versus person conflict and an antagonist and a protagonist and a denouement. You don't need any of that. Just a sentence or two to explain this graph. It doesn't even need to be in proper grammatic form. You can just put it in point form. I don't care. But when I give you this test, some of you are going to spend an hour and a half writing the scenario. And then you're going to be like, I need more time! And you're going to hand it in. It's going to be like 5 pieces of paper. Here it is. Yeah, exactly.
It's a tragic story.
Yeah, it's so tragic. You would not believe the ins and the outs of water in a watering can. I only bring this up because, as I say, every year, every time I tell you guys something like this, it's because I've had more than one student do that. Like literally write a novel for a question like this, then tell me they don't have enough time to do their math class. There was once a rusty watering can languishing in the garden behind my great-grandmother's house. My great-grandmother had fallen ill that summer, and her beloved garden had become untended and wild. I felt a deep melancholy at the fact that my great-grandmother might pass that summer. And I felt that the most fitting tribute that she may leave to the world would be one more summer of beautiful wildflowers in her garden. And as a result, I took it upon myself to tame back the wilds and bring Grandma's majesty back to her little corner of the planet. So I picked up the rusty watering can. Anyways, you get the drift. It doesn't have to be like that. Although that was pretty good.
10 years from now, we'll go back on it.
Yeah.
Video.
All right, so how many sections does my scenario have to have? 3. The first part right here, what's happening? I'm filling it up. Was it empty? No. So, section 1, I got a partial watering can. Partial watering can that I'm filling up. How many people spelled partial wrong? Just checking. What's the second part? That's here. There's 1. What's happening in 2? What could be happening?
The water is staying there.
The water ain't going anywhere. That's a pretty boring scenario. Okay, sure. I had to answer the phone, and I'm not an idiot. I don't want to waste no water, so I turned it off. The point I'm trying to make is the can is full. Right? That's as full as I'm going to fill it. I got a liter in it, 1.75 liters in there. Okay, it's full. Do I have to add in that I answered the phone, that I walked across the room, that I was looking for the right ficus to water? No. Can is full. What is happening in section C? You are emptying the can. Now, somebody always says, Mr. Myers, if you're emptying the can, doesn't it all just go out at once? It is not Star Trek, kid. They do not beam the water out of the watering can and then beam it to the soil. It must fall. While it is falling, time carries on. Does everybody understand? Okay? Yeah? All right. Please notice a few things here. What is happening here? Time is going on, yes? And what is happening to the volume of water in the watering can? It is going up, right? It goes up 0.75 of a liter in 30 seconds. Does everybody understand that? So what does that slope tell us? It tells me that if I wait 30 seconds, I will get 0.75 of a liter, won't I? What if I wait a minute? I'll get 1.5 liters, right? What if I wait 5 minutes? Oh, that was a hard one. I'll make it easier on you. What if I wait 2 minutes? 7.5 liters for 5 minutes. Everybody with me? That slope tells me the speed at which something is happening. What do you notice about this slope? It's steeper. So what does that tell you is happening to the volume of water? Is it going faster or slower? Faster. Why? Shorter period of time and greater loss in volume. Do you understand this? Oh, good. That makes me so happy. Okay. Some of you have already done science, which means you're not going to screw up number 3.
Just right now. Yeah.
Some of you haven't done science, so you're going to screw up number 3. If you've done science, Don't help the people that haven't. Do this question in pencil, because 90% of you are going to screw up part of it. Okay? See if you can do it. I'm only going to give you one hint, and I'm not even going to say it out loud. And now I'm going to sip my tea and wait patiently to see how many of you know what you are doing or are able to figure it out. Some of you, like you just told me, are doing this right now in science class. Who is teaching you science? Mr. Radnai?
Yeah.
He's a rad guy. Joke never gets tired. These are wrappers from the, quite frankly, disgusting Chinese treat that my Chinese exchange student brought back from China for us. It's a disgusting Chinese treat. Olives. They taste a little like flat. I like olives. These taste like flat cola. And there's a giant pit in the middle of them. You're welcome to try one. I told some of my other class about it yesterday, and they were all like, oh, we want to try it. So I brought it in. They're olives. That tastes like flat cola, to me.
Like Coca-Cola.
Yes, Coca-Cola. Would you like to try one?
I'll try one. Yeah.
They're from Taiwan.
Yeah, we'll try.
There's a giant pit in the middle of it, which you will have to deal with on your own. Would you like one?
Horrified. I'm actually horrified.
Your mom loves them. Here you go.
Oh. It's like a raisin.
I think it tastes like flat cola.
It does. It does.
Please, I don't want them. I have now learned that anything my Chinese exchange student offers me that is food-based, I am saying no. Right? In the summer, he brought my wife chewing gum. She was chewing it, and he waited like 10 minutes, and he said, ma'am, because he calls us sir and ma'am, do you feel drunk? And Catherine was driving. She's like, no. Should I? Then he gave that to my kid today. I didn't know what it was. It's disgusting. It tastes like horse's butt. And my son says, oh, sure, I'll try a candy. And I knew what it was. I didn't want to say anything. I was like, no! St. John puts it in his mouth. And he waits until Sean gets out of the car, watches him walk away. And as soon as he's far enough away, St. John rolls down the window. It's so disgusting. I don't know what it is, but it's grody. Yeah, if you guys like them, that's great. Huh? You want to try one? Here you go, buddy.
What do I do with the pit?
Yep. You can throw it. You put it in there. I'm dumping them.
Taylor actually likes them.
Who?
Taylor.
You're messed up.
What are they called?
They're olives.
Why are there so many of them?
I don't know. There's 1 billion people in China. There's a lot of olives.
No, I like my salty. Ew. I like meat. Probably do this. What are they called?
I'm going to say it for the 75th time. They're olives.
They just taste like a dried fruit. Yeah.
I disagree. Don't eat the plastic.
Just pour them on your mouth.
Pleasant, aren't they? No. I know, right? Did I ever tell you guys the story about the Mexican candy?
No.
I was at a Mexican grocery store in the States, and my kid's like, "Oh, Dad, look, Fun Dip, we want this candy." And I was like, Mexican candy is different than ours. And the lady at the counter's like, "They don't want that candy." And they're like, "Yes, we do, yes, we do, yes, we do." I said, "If I buy this candy, you're going to have to eat all of it." They're like, "We will, we will." It was Fun Dip, but the dipper tasted like tamarind, and the powder wasn't sugar, it was spicy. Like, painfully spicy. I don't know how Mexico has become the second fattest country in the world if their candy tastes like that. Yep. Yep. Yep.
Where are we on that scale?
We're like third.
Nice. We are?
Yeah. But we live where it's cold. We need to have some blubber. All right. Here we go.
I didn't even draw it. I was just being we're distracted by the
What goes on the horizontal axis? Time. Yes. Because for everybody else in the world that isn't visiting their grandma, time is still passing. What goes on the other axis? Distance. Excellent. Now, at 0 time, how far has Jack traveled? 0 distance. Excellent. The first part says Jack spends 2 hours driving 140 kilometers at a constant speed for 2 hours, which means how far does he go in 1 hour? 70. So there's 70. 2 hours. I got to go up twice as much. There is the first bit. Now, is that an actual representation of Jack's drive? No, of course not. Why? Did Jack drive out of his driveway at 70 kilometers an hour?
Maybe.
No, he didn't. Did Jack manage to maintain exactly 70 kilometers for 2 hours? Of course not. There were stoplights, there were idiots, lane change, there was somebody who got in a crash and everybody had to slow down and look at the crash when they drove by, even though it was already off to the side and ruined traffic for everyone else. But that's how we draw the graph. Is everybody cool with the first part? Everyone is good? Okay. Jack visits Grandma for 1 hour. What must happen? A horizontal line. Why? Because he's not going anywhere, but time marches on, just like the Metallica song says. So there's A, there's B. Now, we are at 140. Jack drives 50 kilometers back towards home, but then stops for 30 minutes for supper. Here is where half of you are going to do this wrong. Where does the line go from here?
Down.
I knew it. Goes up. Why? He's traveling more distance. Doesn't matter that he's going home. That's displacement, which we're about to talk about. So right here, he drives another 50K. Doesn't matter that it's back home. So now we're up to 190, yes? And it takes him how long? Do we know? No, we don't. So if we're just sketching a graph, as long as we go up 50K in a certain amount of time, I'm happy. Everybody with me? What happens after 30 minutes, which would be at 3.5 hours? What happens right here at 3.5? For how long? 30 minutes until 4. Everybody cool with that? Goes flat. And then he returns home, taking 2 more hours. So home is another, how we have to end up at 280, don't we? Because it's a 140-kilometer trip each way. So we're going to end up at 280. And this is going to take 2 more hours. So we're going to go out to 6, go up to 280, there. That is what the graph needed to look like. How many people got it right first try? Or close to? How many people turned back when I used those words, turn back? Some people turn back, right? Here's why. First thing we're going to talk about is distance versus displacement. Distance is what we call a magnitude, because it is simply a quantity. I am going to go that way. Everybody got it? Count my steps.
2, 3, 4.
Now I'm going to go back that way.
5, 6, 7, 8.
How far did I travel? 8 steps. How far have I been displaced? 0. If you had your eyes closed and I went like this, and I was right back here, would you know if I had moved or not? No. My displacement was 0. My distance was 8, but my displacement was 4 positive, 4 negative, and I end up back at 0. Understand? Now, the problem here is, for me, that's positive. Why? Because it's to the right. What is it for you? Negative. So displacement is always measured from a reference point. Okay? Because displacement is what we call a vector, because it has a magnitude and direction. And math and physics guys have come up with a few rules to follow for this. A positive displacement is right, north, east, up, away, forward. I can't think of many others. Can any of you? Is everyone okay with that? Does that cover enough for us? And a negative displacement is the opposite of all those. Okay? So left, south, west, down, returning, and backwards. Is everybody cool with that? So, if I come back up to the graph we just drew, and I want it to be displacement, which I'll draw in blue, what happens right here? What happens to all of these lines? They just reverse in the same. They're just a reflection, ending up back at 0 where I started. Does everybody understand? Distance versus displacement. Is everybody cool? I'll give you yet another example. If I run around a track 10 times, how far have I run? Somebody in here has run around a track. How long's a track? 400 meters. If I run around it 10 times, how far have I run? 4,000 meters, which is 4 kilometers. How far have I displaced myself? 0. Everybody understand? The Indianapolis 500. 500 miles around a circular track. How far do they displace? 0. How far do they drive? 500 miles. Got it? Everybody cool? Okay. Now you will notice up here I've also included this, rate of change. Rate of change is always the dependent variable divided by the independent variable. Which you guys, in this graph, what was my dependent variable? It was kilometers. What was my independent variable? Hours. Kilometers per hour. So my rate of change gave me what? What do we measure in kilometers per hour? Speed. Okay, your rate of change on a distance time or on a displacement time will give you your speed. If it's a distance time graph, it gives you your speed. If it's a displacement time graph, it gives you your velocity. What is the difference? Pardon? Velocity has not distance, but direction. Okay? So if I go this way, for me, that's positive, right? So this is a positive velocity. Understand? If I go back this way, it's a negative velocity, but it's still a positive speed. Because speed can never be negative. Everybody with me? Everybody cool? Okay. So, what happens here? Now that you've done one, what happens here? Is that displacement or distance? Look closer. What? Look closer. Look closer. It's neither, is it? It's speed and time, right? So what happens? What happens for the first 2 seconds of the race? She's getting faster and faster. What do we call that? Increasing speed. What's the one word for that? Starts with an A. Acceleration. So she, for the first 2 seconds, she accelerates to top speed. What is her top speed? 8 meters per second, which is damn fast. In case you care, that's almost 30 kilometers an hour. It's like Olympic sprinter speed. So that's for the first 2 seconds. How long is the race? It's a bit of a trick question. How long is the race? It takes her 16 seconds to have no speed. How long is the race? 14 seconds. Why?
She goes as fast as she can.
If she stops in the middle of her race, I'm going to lose anyway, and I'm a millennial, so I'm just going to walk. But she doesn't keep going around because her speed at this point case is 0.
What if the race ends at 8?
If the race ends, you're right. The race could end at 8 seconds, couldn't it? And she could be doing that thing where I'm just taking, the victory lap. You're absolutely right. You're absolutely right. Yeah, a half a victory lap. Now again, somebody always says, but if she stops running at 14 seconds, why is this a slant? Because she didn't run into a brick wall. She had to slow down. You can't go from moving 8 meters a second to 0 instantaneously, unless indeed you run into a wall. And even then, technically, it's not instantaneous. You're mushing. So first 2 seconds, she accelerates to top speed of 8 meters per second. What happens then? She runs how long? For how long? She runs for 12 seconds at top speed. And what happens at 14 seconds? She starts slowing. At 12 seconds. And she stops, not 12, 14, sorry. She stops at 16 seconds. Got it? Easy peasy lemon squeezy, right? So you guys do 5, 6, 7, 8. And I'm done. You're going to do 5, 6, 7, 8, and you're going to do 281 and 295 for homework. Or right now if you want. You're going to do these next pages of notes, and on the outline on the front of your booklet, you're going to do 281 and 295. Okay? Look, be very careful with number 7. And also remember, guys, the key to these graph questions, they are sketched, okay? You do not need to get out a ruler. You do not need to get out graph paper, just like what we did here. That's all I'm asking, okay? It doesn't have to be pretty. It doesn't have to be perfect. I'm after the concepts here, okay? I'll let you draw perfect graphs in physics class. All right?
We had one that said you were paddling a kayak at 7.5 feet a second.
Yeah.
That's really fast for like someone to paddle.
I don't know.
If it's just you in a kayak, I mean, if it's a kayak team.
But it says it's just you in a kayak.
Well, 7.5 feet per second.
It was 350 kilometers an hour.
7.5 feet per second, right?
Yeah.
That is 27,000 feet an hour. 27,000 feet times...
Where does that kid go?
that is 5 miles an hour. Which is still pretty darn fast to be paddling.
Yeah, because we had to break it down to 7.5 feet, so at 350 kilometers an hour.
It was meters, and I just did it in my head kind of. Oh, so it was about 7.5. But
Meters per second to get to kilometers per hour is times 3.6. That's the easiest. Number 5 is like my favorite graph because people do it wrong all the time. It's a game. We played the dice game at the beginning of the year. Sure we did. You roll the dice, you add your score. If you're standing and I roll a 1, you have to sit down, you lose your points. Really?
nope.
Oh.
Played that.
We must have played something else.
We've never played a game. Yeah, no, we've never played. We played gummy bears, that's it.
Really?
We do numbers, that's it.
That's mean of me. Maybe we'll play some skunk. Leighton just writes on there. At one point, Leighton had like 45,000 gummy bears. He just writes on it. Leighton's a funny guy. First person to try the olives today. You want a whole pack? I don't really like them.
No, they just taste like a dried fruit.
The taste is still in my mouth. It's like it's sad.
It hurt my teeth because the punk didn't tell me there was a pit in the middle of it. He didn't tell me what they were. He just said these are Chinese. Actually, he didn't. He said they're from Taiwan.
How long does it take a kid to swing up?
All right. Number 5. Somebody has graphed this because I asked them to. What does it look like? Yes, it must go like this. The height starts low, goes up, then down, then up, then down. Somebody always graphs it this way.
What?
Because the swing goes that way. Forgetting that I've spent like an hour talking about how time can't go backwards. Somebody always graphs it that way. Who's the person? Somebody graphed it that way. Who did it?
Time traveling swing.
Yeah, time travel. My son just said, you know what would be awesome? If you could invent a bungee cord that when you jumped off something high enough, you went back in time for like a second, and then you came back to the normal. I'm like, oh my God, shut up. You're such a doofus. He's like, I know. Okay, so I'm glad nobody drew that wrong. Right, McFly? Anyone? McFly? One person got it. Back to the Future, McFly. Knock, 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 McFly. All right. Distance and time for a 400-meter race. What goes on the bottom? Time. What goes on the side? Distance. What's at the top of our graph? 400. Does it matter what I put for time? No. Let's say it took 2 minutes. Boom. Done. Right? That's assuming what? That's assuming a constant speed, then that they didn't stop. If it were a race, would it look like that? No. What would a race probably look like? Do you start at full speed? No. You start a little slow, accelerate, then what? You get the top speed and try to stay there as long as possible, right? So we still carry on, carry on. What happens when we get in sight of the finish line? What should you do? You should speed up, shouldn't you? Your big finishing kick. Not like you millennials. Oh, there's the end. I'm just going to stop. They're going to give me a ribbon anyway. Super fast at the end. All right. Now, number 7, I said to watch out for. What's the difference? Why is number 7 different? It's displacement, isn't it? What does a track look like? It's a circle? It's an oval.
All shapes are close.
I want to find a circle track now. See, like tracks can be circles. I'm gonna Google that by tomorrow.
A triangle. Hexagon.
Depending on where you start, does it matter what shape your graph will have? No, it will just depend on where your graph starts, yes? As I start running here, that way, what does my displacement do? Does it go up or down? Up, right? What happens as I start turning the corner? It continues to go up, right? What happens when I get around to there? Where should it be? Will it have come back down? On a displacement graph, will it have come back down? Yeah, why? Because isn't that point closer than that point? So the graph would have to look like this. Away, 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 back towards. And then what happens as we go around here? Away again, away, 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 to the same peak. And then what? Back to the start. Everybody understand? Okay. And finally, you got to do that. Wait a minute, Myers. Position time. Which is position? Distance or displacement? You can't just say the first syllable. They're both the same. Displacement. Distillacement, Mr. Myers. Distillacement. Which is it? I'm not telling you. You have to do that. I'm not telling you. You have to do that. Hey, Mr. DeVries.
Hey. What's Leo's last name?
Wong.
Thank you. Go figure.
Yeah. Oh, crap. That reminds me.
We travel back to school. We don't drink this. And it's just like that. Either way, it's that. No, because your position would be the same. If you go back home, then it would go like that. So you get to school and turn around and go right back home. We could write oh yeah, and then home. We'll draw like a little gap like this, and then go for 6 hours. Amazing. Quality graph. Right?
Graph of my test versus my assignments.
Yeah.
Assignments.
Well, like one of those tests is like 2 weeks long. Just like, yeah. No, because you start at 100%. No, because you don't start at 0%. You're going to school. You go to school, you get to school, you come
Everybody, this is Mr. DeVries. He'll be your teacher next year.
If you're lucky.
as you travel to school.
Okay. So, really lucky.
Okay, then you're not coming home. Then stop there. Just forever.